Well, thank you. Today I want to talk about this example. So this is a hypergeometric equation. You look on Schwarz's list. It tells you which of these have algebraic solutions. You see that this has an algebraic solution. And here's the minimal equation of such a solution. And so I'd like to talk about how one goes about finding this. I'm going to turn this off because, in fact, it just makes you crazy to look at it. But we'll come back to it. Oh? No. Excuse me? Yeah, there was some root that. So, what the last lecture I talked about Jordan and his idea. So Jordan's idea was you are looking to decide if an equation has algebraic solutions, assuming, let's say, it's irreducible. His idea was to use the structure of the group without knowing the group. So you have enough information about the group. You don't have to determine the group, but it's enough to decide if it's algebraic. Fuchs's idea Fuchs was working around the same time. His idea was that if you know the group, plus a little bit of invariant theory, this should actually give you the equation of a solution. But for Fuchs, he needed to know the group. And today what I want to show is I want to take Fuchs's idea and show that you can also calculate the group. So I'm going to replace Fuchs by Tanaka plus, that is, gives the equation. I'll explain what I mean. So this theory that I'm going to describe it's the following idea. So invariant theory is a piece of representation theory. You're representing your group acting on polynomials. You could just have your group act on vector spaces in general. And so this Tanaka piece will be somehow representation theory gives you the equation. So theory yields the group. What do I mean? So I want to address two questions. The first question is, how does representation theory determine the group? And the second question is, how does a linear differential equation yield the representation theory of its Galois group? So there are two issues. Eventually, I'm given a linear differential equation, and I want to get the Galois group. And the intermediate step will be the equation, from the equation, I can get the representation theory of the group. And from the representation theory of the group, I get the group. And there's something a little nutty about this. That is, what is a representation? It's a way of representing your group as a group of matrices. Well, if you know the group of matrices, you know the group. So I have to say it must be a little more subtle. Okay. So I'm going to address these two issues, and then at the end, I'm going to show you how this philosophy can be used to compute. It's not just a dream. So let's first just look at group theory. So I'm going to start with a linear algebraic group. So it's think of it as a group of matrices somewhere that are determined by polynomial equations and n-squared variables. And this is defined over C, some algebraically closed field. And I'm going to look at, this is the category of finite dimensional G modules. So what is that? That's just, I'm thinking of ways of representing G as n by n in the as linear transformations on a vector space. V is finite dimensional C vector space. Okay. And I don't have a basis. It's just some vector space. And you can do lots of things with these modules. If I take two modules in here, I can form direct sums. There's a natural way in which G acts on this. I can form tensor products. I can think of sub-objects. I can take duals. Okay? So the objects are these things. The morphisms are linear maps that preserve the group action. So if you have a linear map on G times V, you're going to get G times the map applied to V. And an interesting thing about this is that this guy is also a G module. That is, if you take a homomorphism, B in here, then and G is in G, you can act on this by saying this is just G of phi of V. So you know, in a category you have objects and homomorphisms, but here the homomorphisms you can think of as being an object as well. Okay. Now, there's a simpler category. I'm going to call it vector spaces over C. This is just the category of finite dimensional vector spaces. Maybe I do, but yeah. Whatever I write down after this may be wrong. It's, I think, yeah, sure. And I'm going to get right and left mixed up immediately, so bear with me. I'm going to erase this, but you can do it in some way. And of course, this also has tensors and sums, and subs and duals, and also one can talk about homomorphisms, just as vector spaces. And what one can do is one can start with a G module and forget that G is acting on it. So I can get a functor from here into this vector space. You just take V and you forget G. So what I'm saying is you take the objects here. So for instance, you take a vector space together with its invariant subspaces, and you put that in here. Now, you're not going to consider all subspaces of V over here. The legal subspaces now are going to be the ones that came from invariant ones. So I'm going to get a subcategory. So what I'm saying is you have a group, and you're looking how it acts on all kinds of subspace, on vector spaces, and there's certain designated subspaces, the ones that are invariant. There are isomorphisms between these guys, but these are only the isomorphisms that come from ones that preserve the action. So you have a bunch of vector spaces, subspaces. You're able to tell from here which are isomorphic, which aren't. You're able to form these tensor products. And the Tanakian idea, and this is in this context, hard to say exactly who it's due to. It's originally, I think, Vedra Ravano. There seemed to, I haven't looked at this paper, there seemed to be some gaps that the lean fixed. And what the lean showed was that just from this side, you can recover G. Just by knowing which vector spaces came from representations and what their structures are, without knowing the original G, you can recover G. And I'm not going to say how. In particular, the images here, you have distinct images, then you have distinct groups. So the takeaway from this is that we can distinguish G1 and G2 by looking at representations. At some point, either two vector spaces which were isomorphic as G1 modules or not isomorphic as G2 modules, or a vector space may have a proper G1 invariant subspace that isn't G2 invariant. Okay? So this is the Tanakian approach to looking at algebraic groups. And I'm not being very precise, but this was the takeaway. Representations determine the group. Okay, what about how do I get this representation theory from an equation? So here I want to talk a little bit about differential modules. Okay. So what is a differential module? I'm going to take a differential field. These have played a role, often not explicitly, in almost everything that was discussed. So this is a differential field. It's a derivative. So let me do it this way. The derivative is prime. Okay? Doesn't make it better, but it'll help with the notation. And I'm going to form this ring of operators. Yes, if you're given the two groups. In particular, I want to distinguish a group from a subgroup. That's the usual situation. And in that case, for that, I will be taking the same view. Yeah. Okay. So a D module. This is the ring of differential operators. It has this funny multiplication, which we've seen. This is how you commute things. So a D module, for me, is a finite dimensional K vector space. Together with an action, M, that does the following. So it's again, we've seen this kind of an equation before, a connection equation. What does this have to do with anything? Well, let's take an example. If I start with a differential equation, let's write A as Aij, and the Aij k. I can give you a D module. I'm just going to take k to the n copies of, this is a matrix, n by n matrix. Okay. I'm going to give you a module. This is the basis, let's say. So I have to tell you what the action of D on the module is determined by the action on the basis. And again, I usually get this wrong. I want D of Eij to be a sum, E sub I. It's minus Aj I Ej. It's little g. That's the matrix. It's the way I write matrices. Yeah, but I'm not using the algebra structure. Okay. And if you work this out, if you have some matrix such that Z prime is a Z, it corresponds to saying that the correctly, d of summation zi ei is 0. Interpret solutions. So I have this, this object, and you can talk about morphisms that preserve the structure, and you can also talk about sums and products. Let me give you a little dictionary here. So if M1 corresponds to y prime A1y, and M2 corresponds to y prime equals A2y, then you can form a sum. It corresponds to y prime is A1, 0, 2y. Get a feeling for it. You can take tensor products. These correspond to Kronecker products. The Kronecker product is, you take an entry here and you multiply by the whole matrix there and stick it in its place. You can talk about duals. This corresponds to minus the transpose. And once again, the homomorphisms have a structure as a D module. And before I write that down, let me just say that the word D module is used in various contexts. Here, the coefficients are from a field. Often when people say D modules, they mean over a ring, but I want to work over a field. Let me just say the D module homomorphisms from M1 to M2, this corresponds to matrices B that satisfy the equation we've seen before. So if you have a matrix transformation from this to this, then in order for it to be a D module map, it should satisfy a differential equation. So this thing is again in there. So there's a matrix that gives you that, they're finite dimensional vector spaces in the suitable basis. Looks like. Now, I want to talk about solutions. And I don't want to do this too formally. But if I have F, a differential field, now, of course, this may not be a finite dimensional K vector space. So I'm leaving my world. Let's not think too hard about it. I can talk about D module homomorphisms from M to F. F here is a differential field containing K. I've extended it. And if you think about this, this is what I want to think about as the solutions of, let's say, if M corresponds to. And for instance, if F is a Picard-Bessio extension corresponding to this would give you the solutions in F. But if it's a Picard-Bessio, the thing we would be most interested in is once you pick a basis, the Picard-Bessio extension associated to that. One can show that these solutions are a finite dimensional vector space over the constants. And as long as the constant field here is algebraically closed and you have no new constants, the solution space and you pick a Picard, I didn't want to get involved in this. This is suitably independent of choices. By what I mean is, if this is some large Picard-Bessio extension or some extension containing enough solutions, and it has a Galois group over K, this object is a vector space. It's a module for that group, and it's independent of the choices you've made. Its solutions in the bigger field F. Vector. If my life depended on it, I could probably be precise enough that it would be correct what I said. I don't want to do that right now. I just want to give you a sense that from such I want to give you a sense that there is another functor from this. Did I give it a name? I didn't. Let's give it a name. E mod. Okay. This is the category of E modules. And there's a functor from this category to vector spaces. And what it is you take a module, pick a basis, write down the equation, look at the Picard-Bessio extension, and look at solutions there. And again, one has to check that all of this is suitably independent. C is going to be the constants of K. M into solutions in Picard-Bessio extension for AY. M corresponds. Okay. There was a lot of choice made here, but it's suitably independent. And in fact, rather, I don't want to say into the vector space. Yeah, to the vector space. And you should notice that, note, these solutions are a G module for the differential Galois group. So I don't want to look at the whole category right now. I want to start with some module M corresponding to M equals AY. And I want to look at the subcategory of so the smallest that's closed under sums, tensor products, duals, subspaces. If you have tensor products and duals, you get homomorphisms. But I'll say it in yeah. So leaving something out. Quotients. That is, if you have two submodules, you can form a quotient. And now I can make this a little more precise. Okay. So if I take one M associated with one equation, I can look at the associated PV extension, and I can talk about solutions there. That we've spoken about. And one should look at these operations. So if I take the sum of two equations, remember I got the new equation A1, A2, and the solution space equals the sum of the solution space of this plus the solution space of the other guy. And now I'm going to write something pretending that it has meaning. So what I want to say is something like this. The solution space of this is the sum of the solution spaces. And the same thing is true of the tensor product. The dual is again the dual of the solution space of the dual module. The dual equation is the dual of the solution space. So if I call these operations constructions from linear algebra, the moral is that if I look at solutions of constructions, it's the same as constructions on solutions. Oh, and I'm not being too precise, but that's the sense you should have. So I start with this D module M, and I'm thinking of some equation, and it has a Galois group G. So from M, I can go to this, go into the vector space over C. I take M to its solutions. And from the Galois group, I had phi too many times, didn't I? Let's call this C. And from the Galois group, I can take a G module, some G module, and I can go into here using my forgetful functor. And the point is that the images are the same. Much more is true, but that is, the structure here of G modules and their subspaces and isomorphisms, forgetting that they came from G modules, is the same as what I get when I look at solutions. So maybe I should do the following in this smallest category. Is that a little better? Yeah. Okay. Yes. Well, I've defined the Galois group of the module to be the Galois group of an associated equation. Turns out that if you take a different basis of your G module, of your D module, you will get a conjugate group. You'll get the same group. I think people say the following: two equations that two equations that are gauge equivalent have the same Galois group. This, yes. So if I start with this, so N is a G module, and when I form all these kinds of constructions, the solution spaces can be gotten from the solution spaces of the original objects. So they act on, so G acts on them. Right. With the relations, that is, excuse me? You have a representation of G where you forget about G. I mean, you have all of the G modules here, but one of them goes to, so N is in this category of G modules. So, the The police calling about your children. What is the point of all of this? And that is, if I have a differential equation and I want to determine its group, so its group is determined by the representations, all of them. But if I'm lucky, I want to distinguish this group from some other group, there may be just one representation that will help me. And the way I get that representation is by taking my original operator, whatever way I got the representation here. By the way, let me say something about that. I take my original operator, do some construction, and look at how its solution space behaves. In particular, what's going to happen is I'm going to be interested in subspaces. And as we know from last time, you get subspaces by factoring. So the thing I didn't mention was this can be gotten by taking, if I have a faithful representation, this is faithful, all representations come from this using constructions. Let me give a moral. I mean, it doesn't tell you how to what to do. It gives you an idea that if I start with a differential equation, the differential Galois group sitting inside of GL and C, constants of K, A in GL and A. This is a faithful representation. All representations can be constructed from this. And that statement says that all representations come as solution spaces of constructions on y prime equals ay. That is, if I'm looking for a particular representation, something that I know, I took my original representation, I took its tensor product 3 times, there was a subspace. I can get that by starting with my original equation, doing the same construction, and looking at the solution space. So the full truth is you can recover the coordinate ring of the group from the representations. And from the coordinate ring, you get the groups, which is what you were saying. You can get the equations. By the way, I should say, there is an algorithm to commute the Galois group of a differential equation due to Reshofsky. It's been worked on. It's even more computationally complex than anything I've mentioned in the last week. You don't want to do that. Yeah. Let me give an example, okay? So I'm going to look at second order differential equations. Okay, I'm going to look at second order equations, and simple ones. And it's in K, but let's make it very concrete. If you have a missing term, or something even weaker, the Galois group is going to be in special linear group. It's a nice exercise. In particular, the missing term is the logarithmic derivative of the Wronskian. This says that the Wronskian is constant. And I said the Wronskian, that's a hint. I'm not going to say more. Okay? And we'll let V be the solution space. This is L of Y of d squared minus A. Again, d is just d dx. And let's say it's given by y1 and y2. And so a useful representation in this context, not so much the tensor power, but the symmetric power. Okay? So I don't know what's V symmetric n times. This is going to be the span of Now, for second order equations, we're really lucky. In theory, this is just some new vector space. If this has dimension 2, the symmetric power has dimension is this m plus 1. So the first symmetric power, which is the thing itself, has dimension 2. The second has dimension 3. A priori, there's no reason to suspect that these are linearly independent. But for the second order equations, they are. If I have something like this, if this is 0, this is a homogeneous form in 2 variables, you can factor it. You always factor this. Homogeneous. If you divide by 1, it's a polynomial in 1 variable, and you can factor it. So if this were 0, these guys would be dependent. This doesn't work so well for higher order equations. I'm not worried about that now. So I said that this should be the solution space of something. So I want to define this. This will be an order m plus 1 operator. And you can calculate it. What you do is really now you can thankfully forget everything I said before. It was just the motivation for this. how would you calculate it? The way I would do it is I would take formally something that satisfies this. So just think of it as a variable. Y double prime minus AY equals 0. And I look at its nth power. I differentiate it. Let's let m be 2. So I differentiate it. This is 2y prime. I differentiate it again. This is 2y prime squared plus 2y double prime. I'm going to write that as 2ay squared. And I differentiate it again. And I think, let me see if I actually wrote it down correctly. No, I didn't. So I get something that involves y squared, y prime squared, and y prime y. Excuse me? But I'm going to use this. And this is the third derivative. So I have 4 expressions that are linear in 3 other expressions. So there's going to be a relationship. And I think I've written that correctly. So L symmetric 2 is the triple prime minus 4AD minus 2A prime. So you can do this. So what? Well, let's look at the possible representations. So I'm going to look at subgroups of SL2. Here we have G. Well, you have SL2. And here, for SL2, so V is going to be, I'm representing it as 2 by 2 matrices. All symmetric powers are irreducible. We know that. Now, what are the subgroups? We can have a group that's conjugate to a triangular group. And there's going to be an invariant subspace. So V, oh, by the way, let me say what the consequence is. All of these guys are irreducible. So here, this has a one-dimensional submodule. So L has order 2, so that means that L factors. The order L1 is 1. Right? We did that in the exercise session. Another possibility is you have a subgroup of the infinite dihedral group. Okay. Turns out V is irreducible, but the symmetric second power has a one-dimensional submodule. let me say that this can be gotten from character tables. If you have a character table of the group, there's a formula for how the symmetric powers decompose. I'm sure there are places to see it, but the place that I saw it was in Hermann Weil's book on classical groups, which is still a great book, by the way. So after this, there are three finite ones. By the way, one can do more. There are finite subgroups in here, but I don't want to talk about that. Talk about the finite subgroups. Yeah. So that the original one is irreducible, L irreducible, and the second one is L2 composed with L1, and you get a factor of order 1. No, it's this factors. The L is, I don't remember. I don't think so. I think it is irreducible. Yeah. So what are the other groups? There's this group which is called this notation. It has the property that if you take this group and mod out by plus or minus 1, you actually get the alternating group on 4 letters. It's called the Schur multiplier. I will write down some matrices in a little bit. Here, the symmetric powers for I equals 1 and 2, these are irreducible, but for I equals 3, you get irreducible two-dimensional submodules. And so for our equations, you have L, second symmetric, irreducible, the third symmetric, and both of these have order 2, and they are irreducible. 3, thank you. And you get 2 more, S5, SL2, S4, SL2, and A5, SL2. And again, these are, when you mod out, you get what you think. And I'm just going to write down what happens here. So you get L symmetric I equals 1, 2, 3, irreducible, and 4 factors. And it has a factor, this one has order 2. And here you get I equals 1, 2, 3, 4, 5 are irreducible, and 6 factors. And so before we take a short break, I want to go back to my original equation. So these have bigger and bigger orders, right?
But
L, this is all for, it's for this operator that I wrote down, y double prime minus ay. So these will have order I plus 1. Or if the group is SL2, so, but if I take a subgroup, it might be reducible. So look at the diagonal subgroup.
now you discuss.
Yeah, well, I discussed all the cases. Okay. Yeah. So let's look at my equation. Remember, this was the equation. And so I should write down the symmetric powers for this equation and see what happens. Well, I'm not going to do that, but Maple does it. So, see. So there's a nice package in Maple, the eTools. You have to declare where you're living, so you have to say what the derivative is. This is the way to say it. And then I've written down L, typed it in, and there in blue you see L. There's a command, the nth symmetric power, it's symmetric power L, comma M. It calculates it. It has a package to factor. It lists factors. This is irreducible. The third symmetric power. And sure enough, you have factors. So the equation, its second symmetric power irreducible, but the third symmetric power has at least has two factors of order 2. So now I know what the group is, right? Just from the representation theory. The original equation gives me access to the representation theory of the group without knowing the group. I can construct various things. If I'm a little clever, I do the right constructions. And somehow by looking at at invariant subspaces, I can determine the group. Invariant subspaces correspond to factors. So you can determine the group by factoring auxiliary equations. So this is a calculation that shows that the Galois group of this equation is this funny version of A4, which I've covered up.
The order of the factors?
Yes, they do. Actually, in this case, it's going to be the least common multiple of these two. These are right-hand factors, it turns out, I think, but I don't know in general. No, I take that back. Here, you compose them. You compose them in that order. So one needs to have, well, one needs to know how to factor. That's not so simple. But you know, this was a calculation done in 1992, where computers still had cranks. So one would hope that, by the way, this comes from a paper with Felix Ulmer, I give a reference, and we do this for order 2 and order 3, we play this game. So I'm going to take a quick break. I now know the group, and we can go back to Fuchs and see how we can calculate the equation knowing the group. So we'll take 2 minutes.
Yeah.
Oh, I'm sorry.
Sorry,
Yeah.
no, sorry, it's
Yeah.
okay. You could have several factors.
What do you mean? Yeah, it's. Oh, I can keep going. Yeah.
Yeah,
Yeah.
and for one
Yes.
factorization, but
Yes.
the order is
The order is unique, and the number of factors is unique.
if the group is different. We can always
So I think it's the following is true. For finite group, all representations occur in symmetric powers. So any representation. Yeah, but for finite groups you can. You can keep. Yeah, you can. In theory, you can keep going. Now, one has to be careful. It's not necessarily true that one representation distinguishes this group from all its subgroups. So for instance, the infinite dihedral group is an infinite number of finite subgroups, finite dihedral groups. I don't think there's one representation where its factorization distinguishes it from all of the subgroups. Yeah, this is not a way to calculate the Galois group in general, but for finite groups, if you're lucky, let's put it that way. So it's a tool, not an algorithm. Okay. I need lights. Yeah, I'm done with that. So, yeah. Okay. So now we can go back to Mr. Fuchs. So he was aware of Jordan's theorem. There's a strain. The publication dates don't match, but he knew Fuchs's of Jordan theorem. So let me recall this. So you have some finite group G. There exists a subgroup where H is abelian, which of course then implies that it's diagonalizable, of some bounded index. And G is in GLN. The consequence of this, which I showed last time, was that if I start with an equation L of y equals 0, there exists a solution such that z prime over z is algebraic of degree less than or equal to j of n. So this is an equation having a finite Galois group. So there exists a function just depending on n, such that if you have a finite subgroup of GLN, it has an abelian subgroup of this bounded index. And let me give an example. So the example is G, which is A4SL2. It's generated by two elements. And an element S, which is a little strange. And this I. So we can write this down. The order of this group is 24. It's twice the order of A4. H, you can choose to be TS inverse. The order of H turns out to be 6. And the order of the size of G mod H then is 4. All of these calculations are done in this paper with Ulmer. Yes. It was a subscript before. Yes. Yeah. It's multitasking. So here's a lemma that's kind of useful. So you have differential fields. You have an element of K, algebraic over E, and satisfying the property that y prime over y is in E. I'm going to call this U. Algebraic of degree equal to R. Then the minimum polynomial of y over E is precisely y to the R minus U. So in general, I mean, just knowing, with roots of unity, y to the n is 1, but the minimum polynomial may be much smaller. But this condition gives you this. And the proof is an exercise. And what you do is you write down the minimum polynomial of u, you differentiate it, use this condition, compare the two, and you'll see that most of the coefficients vanish. Okay, so what does this mean? So for the equation that I had written down in my example, we had this second order equation is differential Galois group was this guy. One has to work a little bit, but it turns out that any solution will have degree 24. I'm going to justify this. Any non-zero solution has degree 24 over C of x. And there is a, so if a K Picard-Vecchio extension, here we have C of x. I take my y solution, let's call it z, z prime over z, algebraic of degree 6. I'm going to get things completely backwards in a second. Not write anything down, but let me write down the intermediate steps. So I have z in here. I have z prime over z in here. And I have that this is 6. This is 6, and this is 4. Right? But this is the one, so I said that there was a solution having this less than or equal. It turns out it's equal here. So there is one. Okay. Yeah. So if you have q of x, q of y is the minimum polynomial of u is z prime over z, it's going to be something of the form y to the 4th plus a3 y cubed plus a2y plus a1 is 0. So that's this. The minimum polynomial of this over this was something of the form something to the 6th power minus something. So the minimum polynomial of y yes. It turns out that all solutions will generate the full extension. That's a calculation that I'm not going to do. It's a calculation that Fuchs did already. Okay, so u equals z prime over z. The minimum polynomial, I said, was 4th plus a4y cubed plus a3y. I have two crazy subscripts. Squared y And I made the same silly mistake here. Okay. That's the equation for u, but since z has this other crazy equation, b squared minus something equals 0, we get the equation for z is going to be, I just multiply everything by 6. So Jordan's theorem gives you a sparsity result, which also helps a little bit. So Fuchs used Jordan's theorem, not the way Jordan used it, but he used it to show that the thing that he's looking for, you don't need to calculate 24 coefficients, you only need to calculate 4. Well, this thing was u. So u is this. We have the equation for u, and okay. So now, Fuchs really liked invariant theory. And he was able to write down the invariance for this group. I mean, in theory, you can do this, I mean, by taking something and averaging it over the group, you get invariance. You can, if you're good, you can use Moline's theorem, Moline's series, which is a generating function for orders of invariance to help you calculate. There are many ways. Ulmer and I, we didn't use Fuchs's matrices. We just took some other collection just to see how things would work. But this is from a book by Carmichael and Miller, an old book, where they had also written down invariance. So at this point, you can find, and I'm going to lie here, but I'm going to lie in good faith. You can find generating invariance. These are, polynomials in Y2. Be a fairly high degree. You can, let's say, 1, 2, and I3. You can find it in many places. I'm going to say it this way, and then I'm going to tell you where I lied. But this works as well. So you express each of these AI as some polynomial in I1, I2, and I3. These are symmetric expressions in linear combinations of these guys as you go over the group. You can be a little more careful as how you do this, but I'm not going to explain. And then you have to find the value of these when you plug in solutions of the differential equation. But this is a symmetric polynomial in solutions. It satisfies a linear differential equation. find. Sorry. So now, let's say these are polynomials in variables. When I plug in my solutions, I should get rational functions. So, I mean, how do I find these? The solutions are some, power series somewhere. But in fact, these things, again, satisfy linear differential equations. There's going to be homogeneous polynomials of certain degrees. You write down that linear differential equation, and you look for rational solutions. And finding a rational function solution of a linear differential equation is not hard. Do it, but it's not hard. So you can find these guys, plug in, and you get the expression that I had before. You find them up to a constant factor. And then you need to check. So you have some constants here, and you need to check that you get a solution. So how did I lie? It turns out that invariants can have high degrees. There's something related to invariant called a semi-invariant. So it's a polynomial that isn't left invariant, but when you make the substitutions by the group, you just get a constant multiple. These tend to be much smaller. The differential equations they satisfy are much smaller in order, so that helps a little bit. And these invariants you can find in many books. This kind of calculation is not a hard Grobner basis calculation. And then this is a question of finding rational or, turns out, exponential solutions of linear differential equations. You really don't want to see the computations. They're in this paper that Ulmer and I wrote, called Liouvillean and Algebraic Solutions of Second and Third Order Equations. It's, if you look at the exercises, there's a long bibliography, and it's there. Lists Fuchs' papers, Jordan's papers, and all the papers. So that's the idea of Fuchs. Once you know the group, then you can reduce it to invariant theory. And knowing the group, we can now do using this Tanakian approach. Not always. Like a violin, you have to know how to play it. Otherwise, it makes terrible music. So really, that's all that I had to say. So thank you very much.